Welcome to my talk about asynchronous filling by Myopic Luminous robots. My name is Tamás Lukovsky. It is a joint work with Attila Hideg. The filling or uniform dispersing problem is defined as follows. We have M robots. They enter an unknown area, which is represented by a graph of n vertices. The graph is connected. For each vertex, the adjacent vertices are arranged in a fixed cyclic order. The robots enter at specific vertices called door vertices. The robots can move to neighboring vertices. In the final configuration, the robots have to occupy all vertices. During the dispersion, collision must be prevented. The robots are homogeneous, they are anonymous, they have limited viewing range, they have limited memory, no explicit communication, and they have visible lights, and they operate asynchronously. They operate in the asynchronous loop compute move model. In the loop phase, they take a snapshot about the surrounding. In the compute phase, they compute to which neighbor they have to move or stay at place, and in the move phase, they move there. There are various settings of the filling problem. In the orthogonal setting, the planar array is divided into pixels. The robots can move to neighboring pixels. All the pixels must be occupied by a robot in the final configuration. When we model the area by an arbitrary graph, then we can model an arbitrary subdivision of the plane. We can model a building where all the rooms have to be occupied by a robot. We can model complex surfaces that must be coated by a programmable method, or we can model a cave system or the street network of a city. The filling problem has been introduced by Young et al. In 2004. They considered the fully synchronous filling problem for graphs, and they presented two algorithms for solving this problem with robots with a visibility range of 2 hops, communication range also 2 hops, and memory requirement of 2 bits. Barameda et al. In 2013 considered the asynchronous filling problem for orthogonal areas. They gave 2 solutions, one with communication and one without communication. An algorithm called talk solved the problem with robots with a visibility range of 2 hops, communication range also 2 hops, and 4 memory bits. And the other algorithm called mute, it solved the problem without communication with robots with a visibility range of 6 hops and 9 memory bits. Barameda et al. In 2008 studied the multiply door version of the filling problem. They gave an algorithm solving this problem for k doors with robots with a visibility range of 3 orthogonal hops and 4 memory bits. The robots were colored by k different colors. In 2017 and 2018, we have shown that in the fully synchronous model, the filling problem can be solved by robots with a visibility range of 1 hop for the single door case and also for the multiply door case. Now I will talk about Luminous robots. This model has been introduced by Peleg in 2005. The Medio et al. In 2006 have shown that in graphs there are problems that can be solved in the fully synchronous model by robots without lights, but cannot be solved in the asynchronous model by robots with lights, and vice versa. There are problems that can be solved in the asynchronous model with robots with light, but cannot be solved in the fully synchronous model by robots without lights. Here we present 4 algorithms for solving the asynchronous filling problem in graphs. The first algorithm, called PEG, solves the problem with robots with a visibility range of 1 hop using delta plus 4 colors and O of log delta bits of persistent memory, where delta is an upper bound on the maximum degree of the graph. The algorithm PEC runs in O of n squared asynchronous rounds. An asynchronous round means the shortest time in which each non-finished robot is activated at least once. The second algorithm solved the asynchronous filling problem with a constant number of colors by robots with a visibility range of 1 hop in O of n squared times log delta asynchronous rounds. The algorithm block solved the problem with robots with a visibility range of 2 hops in O of n asynchronous rounds using delta plus 4 colors. And the last algorithm solves the multiply-door filling problem with robots with a visibility range of 2 hops in linear number of asynchronous rounds. These are the first asymptotic bounds for the asynchronous filling problem. Only termination infinite time has been proven in previous works. All algorithms use the follow the leader concept. There are 4 states for the robots. When a robot is placed at the door, it is in non-state. When a robot in non-state at the door sees another robot with a neighboring vertex, it becomes a follower and it will follow this robot. Otherwise, the new robot will be a leader. The leader mimics a DFS traversal of the unknown graph. It moves to unoccupied vertices, and when the leader cannot move, it has no neighboring unoccupied vertex, then it switches to finished state and its successor becomes the new leader. The algorithms use the virtual chain concept. The virtual chain is the path of the current leader from the door. An invariant of the algorithms that all non-finished robots are on the virtual chain. The main task to solve is to prevent collision. Let's see the PEC algorithm where the robots have 1 hop visibility range. The leader moves to unvisited vertices. It is guaranteed that movement is only allowed in the so-called packed state. In the packed state, each follower is immediately behind its predecessor. All vertices of the chain are occupied by robots. The leader only moves when the packed state is reached. In this state, no other robot can move, and the collision freeness is guaranteed. The PEC algorithm uses delta plus 4 colors. Delta is an upper bound on the maximum degree of the graph. So delta colors are used to indicate the direction of the target vertex relative to the entry direction in cyclic order of neighbors. 2 colors, conf and conf2, are used for confirmation of the direction. Robot can only move if the successor is behind it and the deer color is confirmed. And the algorithm uses 1 color, the move color, indicating the movement. Additionally, when the light is off, it is also considered the additional color. The leader moves to an unoccupied vertex, unoccupied neighboring vertex, if such a vertex exists. If there is no unoccupied neighboring vertex, then the leader switches to finished state and the successor becomes the new leader. This procedure is called taking the leadership. So, the rules for the leader, in something more details, the leader can only move to an unvisited vertex. When it wants to move, it shows the direction, setting the corresponding deer color, and it waits until its successor allows to move by setting its conf color. During the movement, the leader shows the move color. When its successor sets the conf color, the chain is in packed state. The rules for follower robots. A follower robot follows its predecessor. The follower robot sets the conf color if and only if, once the predecessor of this robot is showing its direction and the successor of this robot, if a successor exists, has set its conf color already. It means that the successor knows in which direction this robot R will move. This allows the predecessor R prime to move to its destination, knowing that all the robots behind R prime have set the conf color, and the robots behind R prime will not move until R prime moved. When R prime is the leader, the chain is in packed state. It might happen that the leader chooses a target vertex V which is unoccupied at the moment when the leader performs its loop operation, but after reaching the packed state, another robot already moved to this vertex V. In this case, the leader has to change the target. If the leader has an unoccupied neighboring vertex, then R sets the corresponding dir color and waits until the successor sets the conf2 color. Then the leader moves to the new target. Otherwise, the leader switches to finish state and the leadership is taken by its successor. Taking the leadership procedure works as follows. When the leader cannot move anymore, its successor has to become the new leader. The leader sets its dir color to delta. The color delta indicates that the leader cannot move anymore and wants to switch to finish state, and the leadership must be taken by its successor. The successor sets its conf color, waits for the previous leader to turn its light off, and then the successor becomes the new leader and tries to move to unvisited vertices. We have shown the following theorem. The algorithm PEC fills a connected graph in the asynchronous model by robots having a visibility range of 1 hop, O of log delta bits of persistent storage, and delta plus 4 colors, including the color when the light is off. The PEC algorithm runs in O of n squared asynchronous rounds. The idea to prove the running time is the following. We consider the time between two consecutive movements of the leader. When the leader has an unoccupied neighboring vertex, this time is divided in 3 phases. In the first phase, T1, each robot in the chain performs a moving step. Then a new robot is placed at the door and sets the conf color. In phase T2, the conf color is set by all robots in the chain, and finally the target change of the leader might be necessary in phase T3. The time for the 3 phases is at most 2n asynchronous rounds. When the leader has no unoccupied neighboring vertex, then the taking the leadership procedure has to be performed, which can be done in at most 5 asynchronous rounds. Since each vertex can take the leadership only once, the time for all leadership taking is at most 5 asynchronous rounds. We can conclude that the running time of the PEC algorithm is at most O of n squared asynchronous rounds. The next algorithm is the modified PEC algorithm, which solves the filling problem by using a constant number of colors. The main idea is that we encode delta plus 4 colors used by the PEC algorithm by a sequence of log delta plus 4 bits, and we transmit this sequence by emulating the alternating bit protocol, which is also referred as stop and wait ARQ protocol. In this way, we obtain that the modified PEC algorithm fills the connected graph in the asynchronous model by robots having a visibility range of 1 hop, O of log delta bits of persistent storage, and constant number of colors. The modified PEC algorithm needs O of n squared times log delta asynchronous rounds. The next algorithm is the block algorithm, which solves the filling problem for robots with a visibility range of 2 hops. When the visibility range of the robots is 2 hops, then the leader can see all robots that could move to the same target. The idea of the block algorithm is that the leader only chooses a vertex V as a target if the one-hop neighborhood of this vertex doesn't contain any other robot with the light turned on, except when the light is showing direction delta, which means the robot wants to switch to finished state. A vertex neighboring to a robot with its light on, except the color delta, is considered as blocked vertex for the leader. The block algorithm fields that are represented by a connected graph in the asynchronous model by robots having a visibility range of 2 hops, O of log delta bits of persistent storage, and using delta plus 4 colors, including the color when the light is off. After this, we consider the multiply door case. In this case, we have k doors, and we maintain k distinct chains. We assume that the robots entering from different doors have distinct colors. There is only one situation which makes a problem without any modification in the block algorithm, when there is a vertex V and 2 leaders are neighboring to the vertex V, and both leaders choose the vertex V as target vertex. For this case, we define a priority protocol. We define a strict total order between the k colors, and we call this priority order. And then the leader with the highest priority can move to the vertex V, and the vertex V is blocked for other leaders. The taking the leadership procedure is modified so that the new leader takes the color of the old finished leader. The block algorithm extended with the priority protocol solves the k-door filling problem in the asynchronous model, robots having a visibility range of 2 hops, O of log delta bits of persistent memory, and using delta plus k plus 4 colors, including the color when the light is off. The block algorithm needs a linear number of asynchronous rounds. We also perform simulations for the algorithms. Here we see the quadratic running time of the PEC algorithm, blue, and the linear running time of the block algorithm, red, in a line graph. Here we see the running times in a star graph. Since the length of the virtual chain is constant in a star graph, the PEC algorithm also has a linear running time. Here we see the runtime on random Delony graphs, where the vertices are distributed uniformly at random in the unit square. We perform 50 runs for each n. Here we see the running time of the block algorithm for the k-door case in random Delony graphs. We have here a logarithmically scaled x-axis and logarithmically scaled y-axis. The simulation results indicate that the running time of the algorithm is proportional to n over k in these graphs. In summary, We have presented several algorithms for the asynchronous filling problem. The first algorithm is called PEG. It solved this problem with robots with a visibility range of 1 hop, with delta plus 4 colors, O of log delta bits of persistent memory, and it runs in O of n squared asynchronous rounds. The modified PEG algorithm solved this problem by using a constant number of colors. The next algorithm, called block, solved this problem with robots with a visibility range of 2 hops in O of n asynchronous rounds. Then we extended the block algorithm for the k lowercase. We presented the first asymptotic bonds for the filling problem in the asynchronous model. Only termination in finite time has been proven in previous works. There is a natural open question: can the runtime be reduced for robots with a visibility range of 1 hop? That was my talk. Thank you for your attention.